I'm not going to finish chapter 13 today. So normally if I finish chapter 13 today, the exam would be next week on Thursday. But I'm running behind schedule here. So I'll finish chapter 13 next week, probably. Then we'll have the exam the week following. And like I said, the nomenclature and the reactions I'm going to give you more time to do. But anyway, we know that this reaction goes to completion. In fact, let's go ahead and calculate what delta G is under standard conditions for this particular reaction. Now, the way we do that is delta G naught is equal to delta H naught minus T delta S naught. Because all these are under standard conditions, so I can't forget that, which I do sometimes forget. And this delta H is for the system, this delta S is for the system. So once we know that, those are for the system, then I'm just going to stop writing that down. But this is not the easiest and the quickest way. You know there's a quicker way of figuring out what delta G is? The quicker way of figuring out what delta G is by using Hess's law and delta G's of formation. And so an alternate way of determining delta G is by doing the sum of nu P delta G naughts of formation of the products minus the sum of nu R, where nu is how many moles you have, delta G naught for the reactants, delta G of formation for the reactants. And so if we use the delta G's of formation, then we can figure out these more rapidly. And so let's try that for this. It's not, always we're going to do this. We need to know how to do it both ways. We'll see. And so using delta G's of formation, let's go ahead and quickly calculate the delta G's for both of these reactions. Oh, sorry. Somebody unplugged it somewhere. Maybe All right, so the first thing is, let's go and take a look at the products. The products here are going to be hydronium and chloride. This reaction is very interesting because did you guys go back and look at why the entries look funny in what example they use in chapter 7? No? Well, probably should have done this for this particular one. Nobody went back to chapter 7 to look that up? Appendix D? Stop. Well, the entries are funny here. I said I'm not going to review much more chapter 7, but let me do this. So we can find it. This is section 7-8. If you go through 7-8, some standard. So this is just trying to show conceptually here with exothermic versus endothermic standard enthalpy of formation. eventually we hit this part and we start talking about ions. I forgot what page, so let's go through page by page. So here, reaction involving ions in solution. So this is page 278. Let's talk about it. So here we see it. This is the first unusual entry. You know, H plus is 0. The reason it's 0 here is because it's defined as 0. So if we look at something like sodium chloride, or if we look at something like HCl, the one I'm going to use is HCl. Sorry, they didn't use HCl here. I'm going to use HCl. And so it goes through, it talks about it here. But let me give you my take on this, basically. And so let's go back to appendix 18. This is one page. We can see it here. HCl consists of hydrogen ions, or hydronium, and chloride ions in solution. So if we do a calorimetry experiment, you know, if I take HCl, dissolve in water, there's going to be exothermic. This doesn't release energy. Will only form the ions like this. And doing this process is exothermic, you know. Let's say, if I do this, you know how much energy I get? I get minus 167.2 kilojoules per mole if I form it from the elements in their standard state. So if I go to HCl, formation of HCl is minus 167.2. And so if I think in the context of a formation reaction, I'm taking 1/2 H2 gas plus 1/2 Cl2 gas. This is going to yield HCl8Q. Delta H for this process is minus 167.2 kilojoules. So how about you Chem 1A guys? Do you guys remember what the problem is? No? The problem is this. Can you form the H plus alone without the chloride? Can you form the chloride without the H plus? No, we form them together. You're going to form H plus and chloride. We form it together. We do a calorimetry experiment. We're going to get this much energy. And so you measure it. The temperature goes up. You figure out how many kilojoules per mole. This is what we get. We get this many kilojoules per mole. Now I want to ask, how much of this minus 167.2 is due to the formation? Because HCl8Q is H plus AQ plus Cl minus AQ. And so this is strong electrolyte. That's what we have over here, strong electrolyte, but I hydrolyzed it over there. This strong electrolyte consists of H plus and Cl minus. How much of this 167.2 is due to the formation of H plus, and how much of it is due to the formation of chloride? Would you say, hey, you know what I have? Unfortunately, I have two unknowns. I have x and y, and I have one equation, x plus y. If you want it mathematically, x plus y equals 167.2 kilojoules. And so I want to solve for x. Can you think of another equation? No. And so if I have two unknowns in one equation, then is it impossible to solve? Normally, say in math, you'd say impossible. I can't figure out what x is. There's no way. I can guess. Should I guess? I'm going to take a guess. I'm going to say half the energy is due to H plus, and the other half is due to chloride. That's just some wild guess. Are you confident in my rule? I'd say 50-50. It's always going to be 50-50 because it's even. 50-50 is even. Would you be okay with that? 83. No. Well, yeah, I agree. I wouldn't be okay with that either. So I'm going to go 80%. 80% of the energy is due to H plus formation. 20% is due to chloride. Is that better? Or is that just some other wild guess? That's some other wild guess. What about 20-80? I'll go 20% hydrogen, 80% chloride? No, that's worthless. Those are just wild guesses. And so it seems this problem is impossible to solve. But it's not. In math, you'd say, oh, we need one more equation. We don't have one more equation. You know, my second question was a guess. 80 or 50-50, 80-20, whatever. We can use, obviously we can use quantum mechanics to try to figure it out, right? But we're just doing this empirically. Now, here, X and Y, the situation in science is, no, we can come up with an answer. You know what my answer is going to be? My answer is going to be 0 and 100. 0% of the energy comes from hydrogen, 100% comes from chloride. 0 and 100. How do you like that guess? And so when I look at this, when I form HCl, I get minus 167.2. HCl consists of H plus, and, well, if I say 0% of the energy comes from H plus, then I got 0 energy, right? That means 100% of the energy comes from chloride. So if I go and look at the formation of chloride, the formation of chloride is minus 167.2 kilojoules. So you're wrong. We can solve this. I just solved it. I solved it. 0% comes from H plus, so 0 kilojoules from H plus. 100% from chloride. So that's minus 167.2 kilojoules of energy to chloride. We just solved it. We don't need two equations. We could do it one equation with two unknowns, and we just solved it. Yeah?
If you use ionization energy and electrons energy, you get the same answer?
No. No, we get a totally different answer. But don't believe that answer. Believe my answer. Okay? Because my answer is consistent with the book. If the book does it, then it's right. Right? If the book does it this way, then it must be right. It must be 0% and 100%. Is that right? No, it's totally wrong. It's totally wrong. And so why does the book do it? It's totally wrong, but why does the book do it? Because it's the type of error it introduces. What type of error does it introduce? Systematic error. And so all the cations are going to be systematically off. If I go ahead and arbitrarily assign H plus as 0, all the cations are going to be off. All the cations are going to be too high or too low. But if all the cations are off in one direction, all the anions are off in the opposite direction, and this is it. This is math and science coming together. If it was just math, you can't solve it. If it's math and science coming together, then you know something. You know something that a mathematician might not know. A mathematician might not know that you cannot form a cation without forming an anion. You have to form both. So if you form a cation, you're off one direction. If you form an anion, you're off the opposite direction. And when you add the two together, the two systematic errors cancel, and we're back to. And so take this. This is off one direction, 0. This is off the opposite direction. But when we add those two together, what do we get? We get the right answer. Do you see that? And so this is what you, in that one page in chapter 7, this is what you should get from that, you know, in your little annotated notes, you know, as far as what it all means. Well, anyway, what was I talking? Okay, I was talking about this because we're looking at the entries here. Now let me go back to what, I want to go back to chapter 13. So let's leave chapter 7 and go back to chapter 13. going back to chapter 13, I was talking about the easiest way of calculating delta G, and that's the second column here. What we've been doing is we've been using the first column, delta H is the formation, and the third column, which is the entropies. We're going to use the second column. You know what the second column is? The second column is delta G's of formation. Standard gives free energies of formation. Standard change gives free energy. And so we're going to just do it this way. And so to figure it out, we just take the delta G naught of formation of the products minus the reactants. And so let's go ahead and do that. In fact, just to save time, I'm not going to write it down. I'm just going to calculate it here. The delta G formation of HClAQ is minus 131.2. Of that, 0 goes to H plus, and all of it goes to chloride. Right? And so what we'll do is we'll just do it as is. So H plus and hydronium are the same thing. The delta G of formation is 0 by definition. And then chloride is, I'd flip back to chloride, but I don't have to because I know it's going to be the same as it. So it's minus 131.2. And so I got 131.2 negative. This is 0. Okay, then I look at delta G of formation for HCl. Delta G of formation for HCl will be well, it depends on what I use. Should I use HCl gas? Or should I use HCl aqueous? Here. I'm going to use HCl aqueous. And so I'm going to get, well, that's, what do I have? I have minus 131.2, minus a minus 131.2, and then I have to look at H2O. Now, if I look at H2O, then something weird happens here, and that is this. If I look at H2O, and this is tricky because this, what's the H2O used for? H2O is used for forming hydronium. When I look at this table, I don't want to do that because this table, is this table hydronium or hydrogen ion? It's hydrogen ion. If you use hydronium in this table, then you have to adjust everything accordingly. And so in this table, we don't write it like this. In this table, we write HClAQ consists of H plus AQ plus Cl minus AQ. And so when we do that, then we see that minus 131.2 minus 131.2, delta G naught comes out to 0 for this. So 0, what should we do with that? Okay, and then the same thing here, you know, even though I told you hydronium and hydrogen ion are the same, it's not going to balance, you know. And so if I write this in terms of hydrogen ion, I got to get rid of this water, otherwise the atoms don't balance. And so if I do this in terms of hydrogen ion, it's going to look like this. HC2H3O2 goes to H plus plus C2H3O2 minus, like that. Okay, and then we do that, and then what does our delta G come out to? Our delta G comes out to, well, let's see. And so, actually, I'm running out of time here, so we'll see next time. We'll do this. We'll continue chapter 13 next time. I need to talk about lab now because we're going to start our lab on Tuesday. And so on Tuesday, make sure you have the proper footwear. I was going to show a safety video, but the safety videos not working. So let me talk about safety first, and then we'll talk about the setup for the lab. And so what you want to do is you want to look for the exits. This is the first thing. And so in case some noxious gas forms, a fire breaks out, just leave. You know, these are all fire-rated walls and doors. And so if a fire breaks out, you know, they just want to isolate it into this room. You know, if it's a small fire, you might be able to smother it with a beaker, but anything larger than that, then just leave. That's not worth it. Because, you know, there are a lot of fuels in this lab, potentially, and a lot of hazardous chemicals. And so we want to get out of here before any toxic gases are formed. And so we have two exit doors here, but what about that door in the back? Is that an exit door? No, that door is always locked. You can't escape out of that door. So that, you know, don't even bother. You need a key to get out. How about the windows? Can you escape out of the windows? No, the windows are motorized. They have locks on those. You know, if a fire breaks out here, they don't want the windows open. They want the windows closed. So the windows are going to seal shut. You can't get out the windows. So you got to escape out this way. And so escape. If an earthquake happens, you know, you got to watch out for where would you go here if an earthquake happens? Well, you probably want to stay away from the glass. Typically, you stay away from but this glass is shatterproof. You know, there's a membrane in there, and so the glass isn't terribly dangerous, but still, you want to stay away from there. You want to stay away from the chemicals over there. So, what they say is they just say, you know, just try to shelter in place if an earthquake comes. I think we have an earthquake drill in October. And then once things have settled down, then we're going to escape, you know, out there and meet out in the field over there. If you look at the sinks, my sink doesn't have this, but your sink should have an eye wash fountain. Every sink should have an eye wash. Do you guys see it? Yeah. What you want to do is sometimes, you know, these eye wash fountains, if the caps are left off like this, that's no good because, you know, sometimes vapor comes in. Take a look. Do you see all the deposits there? Are those hard water deposits or are those chemical deposits? So, you know, for the eye wash fountains, you want to just make sure there's no contaminants in there to spray them out in case you ever need them. If you get something in your eyes, then usually you can't see, so you got to feel around. If you see somebody feeling around for the eye wash fountain, maybe grab it for them, give it to them, so they don't waste any time. And they spray it. It used to be, I used to work with noxious gases all the time, and even with goggles, those would irritate my eyes. So I would periodically rinse my eyes out, you know, just because they started getting irritated. So you could do the same thing, you know, if you get some irritant in there, you want to be careful. But if you do get a chemical in there, let's say a drop of chemical splash in your eyes, how long do you want to rinse your eyes for? What's the minimum amount of time? 15 minutes. 15 minutes is agreed upon. And that is, if the chemical gets in your eyes, it usually gets absorbed into the eye. And it's like trying to wash off a wet sponge. If you try to wash off a wet sponge, it's going to take 15 minutes to wash off. So that's 15 minutes. We also have an eye wash over here, too. Okay, the eye washes can also double as safety showers. So if you spill some chemical on your arm, let's say I spilled some acid on there, I just wash it off with the eye wash or the tap. The eye wash gives a powerful, you know, spray. So oh, sorry. So this is better probably than this. This is pretty weak. Oh no, it's not that weak either. Whatever's more convenient. If you get a large spill, then you're supposed to go. Well, you could use that too. If you get a large spill, just start rinsing off the spill. But you're supposed to go underneath the safety shower here. If your clothing catches on fire, you know, they say don't bother with a fire blanket over there. Just use this. If your clothing catches on fire, douse the fire with water. All right, sometimes the chemicals get absorbed. Like once I was camping, and I had a pot of boiling water, and I was wearing boots because I was hiking. And I spilled the water and it got on into my sock and into the boot. By the time I took off my boot and the sock, I got a 3rd-degree burn on my leg. It was just small. It was really small, so it was terrible. And lots of 2nd-degree burns. And so if you get chemicals on your clothing, they're going to cause burns. So, and it depends on how bad. Obviously you go there, but you saw the video where they tell you to strip off your clothing, otherwise the chemicals might strip off your skin. Well, if it's not that bad, we also have a private shower, which is located in between the lecture rooms over there. So if you did spill something, it's irritating, but it's not so bad that you're going to strip down naked inside the lab, then you want to go over there and do that. Okay? So that's an option. Now, let's see, what else do we need? No, there's a fire extinguisher over there and a fire alarm, but like I said, if there's a fire that breaks out and you can't just smother it with a beaker, then just let it burn. Let it burn out. Don't try to put it out. And don't try to put it out with a fire extinguisher. They just say evacuate. That's the safest thing. Because you don't know, you don't know what kind of chemicals are in here, how reactive they are, because it could easily lead to a potential explosion. So if you're trying to put out this fire, it comes into contact with something that's explosive, then it's not worth it at all. All right, we're going to talk about contact. Do you see all these hoods? We have a lot of hoods in here, and when we're using hoods, we're generating either toxic gases, or we're dealing with things that could create toxic aerosols. And so sometimes if we're weighing something like chromium, if we're weighing like chromium 6, you've heard of chromium 6 before? There's a movie about chromium 6 in water. Have you heard? There's an activist, Erin Brockovich. Have you ever heard of her? No? Erin Brockovich? Well, chromium 6, do you think that's healthy stuff or unhealthy? It's pretty unhealthy, and it's a fine powder. It's like fine, like pastry flour, And a little breeze here, and you get a little cloud of this coming around. And so, if it's going to generate a cloud of dust, you don't want to inhale that dust. And so, things that are really toxic will throw balance inside the hood, and you can weigh. So if you form a dust cloud, at least it'll get sucked through our filters, rather than, if you form a dust cloud, I've seen this happen over there. If somebody forms a little dust cloud and everybody standing around there is inhaling the toxic chromium 6. In fact, our first lab, we're going to use chromium 3. The chromium 3 is still pretty toxic stuff. You don't want to touch it. Chromium 3 is also a suspected carcinogen. They use a lot of chromium compounds to tan leather and do that other stuff. So a lot of people handle chromium compounds all the time, but we just want to minimize contact. All right, and so what is our first lab? Our first lab is going to be a synthesis, and what we're going to do is we're going to synthesize a complex. And we want to do some preparation before the lab. And the preparation before the lab is this. You'll have your lab notebook, and so on the cover of it, can you just put your name? A lot of people don't write their name, so I have no idea whose book it is. And maybe, just the class, Chem 1B. This way, if you leave it somewhere, somebody might return it over to the stock room. So, and then on the first page, you could write on one side or both sides. A lot of people, what they do is they write on one side. They leave the other side blank for random notes here and there, or miscellaneous information. But it's up to you. And so for page 1 or page I, you would leave this for the table of contents. And so it depends on what type of, if you got the cheap notebook, there's no table of contents there. If you buy a fancy notebook, there's already a table of contents there, like a $10 notebook or a $15 notebook. And so, and the pages are numbered. In a cheap notebook, the pages aren't going to be numbered, so you're going to number them yourself. So page 1 or page I, table of contents. We probably just need one page for that. And so we'll go on to page 2. For page 2, what we're doing is we're going to do a synthesis, and we want some kind of title here. So synthesis. And we could use the title verbatim from the lab. And so what lab are we doing? Let me show you which lab. What do I do here? It's going to work or not. Uh-oh. I grabbed the wrong binder. Oh, stock room. The lab is the synthesis of a transition metal complex. Does somebody have the title?
Synthesis of a transition metal complex.
Synthesis of a transition metal complex is the title? All right. There are 4 transition metal complexes that are synthesized in that lab. We're only going to synthesize one. And so I'm going to narrow down the title. I'm going to say synthesis of a chromium complex. Synthesis of a chromium complex. And so what we'll do is we'll put the title here. This is the chromium complex. And then here we might put a purpose, we might not put a purpose. The purpose is to synthesize a transition metal complex, chromium complex. That's the purpose. Beyond that, we're also going to learn about some chemical reactions. In fact, we're going to do all 3 chemical reactions in here. What types of chemical reactions do we have? What are the 3 types of chemical reactions? Redox, acid-base, and metathesis. And in fact, we're going to do those. Redox, acid-base, and metathesis in that order, in fact. And so purpose is to learn a little bit about transition metal complexes and learn about redox, acid-base, and metathesis reactions. All right, so we can, this purpose, that's not the most important thing I'm going to look for. Then what we're going to do is we're going to divide the page like this. On the left side of the page, we're going to write the procedure. On the right side of the page, we'll write our observations. The procedure, I don't want you to rewrite the procedure in the book. The procedure in the book is too long. When you're in lab, you want to do things quickly and efficiently, right? And so you don't want to be reading, okay, get this beaker, get that beaker, wash that, do that. And so what you do is you'll just condense it down. You can eliminate a lot of the words in the procedure and just have short phrases. Or what I like to do is I just like to draw pictures. And so tell me what the procedure says. Does somebody have the lab manual? They can just read out the procedure for the chromium complex. Or just let me borrow their book for a second and I'll just do this, or read it out or borrow it. Oh, yeah. Okay. All right. Thanks. Oh, sorry. There's something wrong with this. This is still working, I think, yeah. All right, actually, the title, this is the lab we're going to be doing. Preparation reactions coordination. Oxalate complexes. Equipment lists like this, you don't have to write. Chemicals, we're not going to write that in there. Structural stuff, skip that for right now. What we're going to do is we're going to just do number 1. This is the lab we're doing. This is a preparation of K3Cr C2O43.3H2Os. The way you'd read this is this. You know, these are waters of hydrate. Those get stuck inside the crystal lattice, like in the void spaces, like tetrahedral, octahedral voids, that type of stuff. These potassium ions are the counter ions to this. The complex is this. It's a complex anion. How do I know? Because we have some potassiums over here. And I know the total charge on that complex anion. It's going to be this. It's going to have a chromium in the center, and then 3 C2O4. C2O4 is oxalate. Each oxalate is 2 minus. We've got 3 of those. This whole thing is 3 minus charge because we have 3 potassiums to balance that out. So it's got to be plus 3 from the potassiums. This is going to be minus 3. Each oxalate's minus 2. We have 3 of those. It's minus 6. That means chromium's 3. And so the way we name this is we call this tri. Now, oxalate, we change the ending. And so this would be called trioxalato chromium or chromate. Well, it's an anion complex, so it's going to be chromate. And then the charge on chromium is plus 3, so it's chromate 3 ion. And so that's the name of the ion. And so when we name an ionic compound like this, an ionic compound, we just say potassium, that's the name of the cation, and then the name of the anion, trioxalato chromate 3. And so this is called potassium trioxalato chromate 3 trihydrate, solid. And so we're going to try to form this as a solid. Okay, this is the overall reaction, but we don't do it in one step. We do it in a number of steps. And so what we're going to do is we're going to read through the procedure and then just kind of come up with like a visual outline of the procedure. And so if I'm trying to do the procedure quickly, then I don't want to be reading anything. I just want to just see it as... And so what I need is a 250 milliliter beaker. So what I do is on the procedure over here, on the left side of the page, I just draw a 250 mil beaker and then just write 250 mil beaker, like this. And then I need to add 3.6 grams of potassium dichromate to this. 3.6 grams of potassium dichromate. What was the formula for potassium dichromate? It's K2Cr2O7. Potassium dichromate. Do you know, can you tell me the color of potassium dichromate? Do you know what color it is? Do you know the form of potassium dichromate? Is it like a paste? Is it a solid, liquid, or gas? What do you think? It's a solid. Do you think it's a powdery solid, like pastry flour? Do you think it's a granular solid, like table sugar or salt?
I think it's a powder. Salt.
Yeah, we call it finely divided, powdery solid that creates dust clouds. What color do you think it is?
Red.
Orange. It's orange. So sometimes I'm over here and I see an orange dust cloud building up over there. Is that a healthy dust cloud to inhale? No, that dust cloud, what's the oxidation state of chromium in that dust cloud? Plus 6. Hey, that's chromium 6. That's Erin Brockovich. You know, they made a movie about her. Plus 6 chromium. people, getting sick off +6 chromium. And then I see this orange dust cloud there, and I'm going, man, they didn't see. I haven't seen the movie either, but they haven't. I heard about the movie. That's it. But you don't want to breathe that stuff. So the potassium dichromate, we're going to weigh inside the hood. That way, if you do make a dust cloud, or if you do spill some on the counter, it's at least contained in the hood. It'll be easier to clean up then. And hopefully the balances aren't going to be coated with an orange powder on there. And so be careful with this stuff, because this stuff is, now, how bad is this stuff? How bad is this stuff? It's bad, right? But how bad is bad? Well, this is why we need, this is the old name for it. The old name is MSDS. Have you ever heard of an MSDS? Do you know what the new name is? It's not called MSDS anymore. It's called MDS. Why? I don't know why they changed it. But what does it stand for? MSDS, MDS, what does that stand for? MSDS is an acronym, and it's an acronym for what? So let's just do the web search. I'm going to do MSDS K2CR207. Well, this is what MSDS stands for. Material Safety Data Sheet, MSDS form. It's called MDS now, Material Data Sheet. But anyway, MSDS is going to contain certain information, like for example this. Health rating is a 4. 4 good or bad? Bad. 4 is the worst, actually, the health rating. Fire rating is Fire rating is 0, but potassium dichromate can cause very bad fires. This is asking, the reason is potassium dichromate is an extremely powerful oxidizer. And to create a fire, you need both an oxidizer and a reducer. The fire rating is just for reducer. And so if you have a powerful reducer, the fire rating is going to be a 4. If you have a weak reducer, the fire rating is going to be a 0. Well, potassium dichromate is not a reducer, it's the opposite. Potassium dichromate is a oxidizer. So if you take potassium dichromate and you mix it with a powerful reducer, you're going to get an explosion, basically. And so this is a bit tricky because this is only based on the reducer, not the oxidizer. Potassium dichromate causes nasty fires, very nasty fires. Reactivity, that's tricky because dichromate's a powerful oxidizer, so why is the reactivity at 0? It depends on how they define it. What are they reacting it with? What type of reaction is that? Obviously, it's not a redox reaction, because if it were a redox reaction, reactivity would be high. But anyway, let's take a look at the MSDS here. So, extremely hazardous in case of skin contact is a permeator, which means it's going to get absorbed into you. Very hazardous in case of skin contact, irritant, etc. Eye contact, corrosive, inhalation, lung irritant. Prolonged exposure may result in skin burns and ulcerations. Overexposure by inhalation may cause respiratory irritation. Severe overexposure can result in death. Inflammation of the eye is characterized by redness, watering, and itching. Skin inflammation is characterized by itching, scaling, reddening, or occasionally blistering. Potential chronic health. These are cute, so just one-time contact or something. But if you're working with this day in and day out, then you have to worry about these. Potential chronic health effects. It's going to sensitize your skin. Carcinogenic effects. It's classified A1, confirmed for human. So it's carcinogenic. Mutagenic effects. And tetragenic effects, does it cause mutation? Does it cause birth defects? Developmental toxicity? And so it's not good stuff. But, the same thing. We have to compare this. We have to see a whole bunch of different compounds. So, like, if you're at the gasoline station, are you dealing with carcinogens at the gas station? Yeah. Tetragens? Now, at a lot of restaurants, you'll see this, because a lot of things that we normally have data. And so it doesn't mean that we're going to get this. What we have to do is we have to minimize exposure, and there's ways of handling this safely. For gasoline, you don't want to be spraying your clothes with gasoline, And the same thing with this. You don't want to be inhaling the vapors of gasoline, because it's a potential carcinogen, to mutagen, etc., tetragen. So we have to be careful. And if you look at the people who use it, a lot of people use this for tanning leather. And so leather tanners are using this day in, day out. They get it on their hands and inhale the dust or whatever. It's a good oxidizer. And so we should be able to handle this safely. And so if you're ever curious about some of the chemicals that we use, you'll want to go through the NSCS. Now, we look at the physical and chemical properties of this. Let's just go down here and take a look at the chemical properties of this, because they gave the chemical properties a 0. Why did they give it a 0? Because if you look at the special remarks on reactivity, reacts violently or ignites with ethylene glycol above 100 degrees. Just ethylene glycol? And so if we had something else, let's say we have propylene glycol, are we safe? If we have ethylene glycol and it reacts violently with that above 100 degrees, this is why we need to know about classes of reaction. Other incompatibilities, combustible, organic, or other readily oxidizable materials such as paper, wood, sulfur, aluminum, iron, tungsten, sulfuric acid, acetone, boron, glycol, sulfur, plastics, it could react violently with. And so any reducer is going to react violently with. So, that. But you can't list everything. Toxicological information, etc. And so my recommendation is, for this, we're going to weigh this in the hood. That way any kind of dust gets sucked away from you, not towards you. Number 2 is, if you want, you should wear gloves. That way that will provide a barrier to protect your skin from any kind of absorption. But anyway, we're going to weigh 3.6 grams. Now, what if you don't get 3.6 grams? What if you get 3.67 grams? Should you get your fingers and take some out and put it back in the bottle? No. And so this is why we have observation. If we don't get 3.6 grams, let's say I got 3.63 grams, hey, that's okay. We're not going to take it out. We're just going to go with it. And so your procedure is how much you're supposed to weigh. Your observation is how much you actually weighed. And so it's 3.63 grams. Now, what else should we take for observation? We should take things that are not widely known. For example, is the color of potassium dichromate widely known? No. If you asked your neighbor, would they know it? Probably not. And so we would say, it's an orange, powder, maybe. Orange powder. And so we'll dump that in the beaker. So let's go back to this. .6 grams of potassium dichromate to a suspension of 10 grams of oxalic acid in 20 milliliters of H2O. And so below this, I'm going to have 20 milliliters of H2O and 10 grams of oxalic acid. Do you know what color oxalic acid is?
Colorless.
Well, a single crystal will be colorless, but it's white. It's a white solid. Do you know about the health hazards? Is oxalic acid a health hazard? You know, you can eat acetic acid. There's no problem. So you can eat acetic acid, but would you want to eat oxalic acid? You can eat citric acid. You can eat salicylic acid.
It causes kidney stones.
Yeah, oxalic acid causes kidney stones. Don't eat oxalic acid. It's not like citric or ascorbic acid or all those other acids. And so there are some negative, adverse health. Well, obviously we're not going to eat it, but we don't want to breathe in the vapor either. And so oxalic acid, you want to be careful with that too. All right, so it says to do 10 grams, but if you didn't do 10 grams, let's say instead you weighed out 10.03 grams, no big deal. You just do that. 10.03 grams. In fact, I don't even have to write it. I'll just point to it like this. And I'm not going to rewrite oxalic acid. The thing is, we want to do most of the writing here, so when we go into lab, we just have to write little things. Because writing in lab is very time consuming. And so if I could just write 10.03 grams white, solid, that may be enough. It's more granular. Here. And so rather than rewriting this, the sentences out here, I'll just draw a little picture like this. And then the orange-colored mixture should spontaneously warm up almost to boiling as a vigorous evolution of gas commences. That means this reaction is somewhat violent. That means when I add my potassium dichromate, do I just want to dump it in all at once? No, I want to add it slowly because it's going to be a violent reaction. And if I dump it on all at once, this is what happens every semester. Somebody dumps it in all at once, this thing foams and gurgles and spills out onto their bench. And sometimes they do it in the hood. And so be careful with that. Just add it slowly. All right, and then we'll just continue on. So you're going to prep this. How long is this prep? It's not that long because let's look. Okay, it starts here and then we go on. This is going to be a 2-day experiment. And so all we're going to do on day 1 is actually about to here. Okay, but it's not, it's such a short synthesis. You can prep the whole thing because that's where it ends. Actually, let's see, unless I skip a page, let's see. Yeah, it about ends there. We're going to set up an apparatus like this. This is a filtration apparatus. I'll talk about that later. And so there's a little bit more, and then it ends. After this one ends, then there's reaction number 2 here. Reaction number 2, which is a copper complex, we aren't going to do. Reaction 3, which is an iron complex, we aren't going to do. And reaction 4, which is a magnesium complex, we aren't going to do. So we're just going to do reaction number 1. And there are 3 reactions in that, and so we'll talk about those reactions next time. For the last part of today's lab, we're going to have you check in. So find a place you want to sit. There's some empty spots over here around there. So find a place you want to sit and then grab the nearest drawer. And then the lab check-in procedure is the same as Chem 1A. You'll fill out the sheet, check the inventory, make sure you're not missing anything, make sure nothing's excessively dirty. Also make sure nothing's broken. If you're missing any items, or if you have any broken items, get replacements today. Okay, if you notice that something's missing or something's broken next week, they're going to bill you for it. Okay, but today they aren't going to bill you for it. Okay, then make sure you write your locker combination in your lab notebook, something that you bring to lab every day. And then turn in the sheet. And